Hi, this is Paladugu Keshav of CSC Data Science. Today, our subject is Basic Electrical Engineering. Today, our topic is a doubly-fed induction generator test facility for a grid fault right-through analysis. Introduction. With the increasing concerns over the climate change and the fossil fuel depletion, exploitation of renewable energy has become paramount in electricity generation. The last 3 decades have been increasing proliferation of wind power generation and much effort and sustainable funding have been directed towards developing larger and better wind turbine power generation systems. These efforts have led to substantial improvements in turbine blades, turbine generators, drive trains, and control methods. Among all of the technologies used for the wind turbine generators, variable speed, doubly-fed induction generation (DFIGs) were dominant installation and large-sized WTs. A silent feature of this technology is that the stator is connected to the power grid and the rotor is fed by back-to-back converters to meet the requirements for variable speed orientation. In DFIG, wind turbine generator rotor speed typically varies by 30% plus or minus 30% around the synchronous speed, uh, and an economic advantage is gained from downsized power converters which requires only a fraction of a total power of DFIG. A length and nature of converted disengagement together with the speed with the vector control can be resumed are critical issues retained related to the fault response of DFIG wind turbines. In the past, grid codes required to wind farms to disconnect from a grid when a voltage dip was detected. As the wind power gradually becomes a more significant part of the worldwide electrical generation, the disconnection of DFIG generators following a fault may lead to the loss of power balance, putting system stability at risk. Revised grid codes now require wind farms to retain the connected during dip and to supply active and reactive power into the network. Therefore, DFIG wind turbine response to grid faults become a key issue for DFIG operation. In general, large DFIG wind turbine generators are equipped with the some fault right-through capability to comply with the revised power grid codes. A common method is application of a crowbar circuit to the rotor slip ring output terminals. When a power grid fault exceeding a set voltage threshold is detected, the crowbar circuit is activated to bypass the power converters. Another right-through method is the use of barking resistors with initial energy outflow of the DFIG and thus hasten the demagnetized process. Other wind farm level FRT techniques employing auxiliary equipment at the wind farm substation have been suggested, such as the use of dynamic reactive compensation to aid network voltage recovery. Regardless, the FRT technique is in use. It is experimentally difficult and costly to test the standard large wind turbine generators under the genuine fault conditions. This kind of testing on a full-scale wind turbine may expose equipment risk of failures. There is a small 7.5 DFIG test facility with the ability to apply the flexible grid fault conditions in a safe, controllable, and repeatable manner is explained in this paper. Test rig includes the DFIG system, wind turbine emulator, grid fault emulation equipment, and flexible control hardware installation. This paper includes two examples of DFIG fault behavior for 0% and 50% grid fault levels as defined in the Great Britain Grid Code. Grid faults and the low voltage FRC equipments. Short circuits in the power equipment arising from the insulation failure, switching surges, or mechanical causes are commonly called power system faults. Grid faults can be classified as single phase to ground faults, phase to phase faults, and double phase as ground faults and three phase short circuits occurring at the various distances from a wind turbine. Among these three phase faults represent most severe type of power network faults and are studied in detail in this paper. Direct consequence of the three-phase faults is zero voltage and the source of fault. Here's the diagram of DFIG wind turbine network connections and example of fault location. After the fault clearance, the network may continue to operate at slightly suppressed voltage during the period of fault recovery until the isolated transmission equipment is restored. The timescales for these periods are specified by each transmission system operator in their respective grid codes. The grid level circuit bank breaker will typically clear an overhead line fault well within 1 second, and it clears a close-up three-phase zero voltage fault with handful of cycles, 80 to 200 milliseconds. The figure shows the typical connections between the single DFIG wind turbine in the wind farm and the GB transmission network. Other countries, the network have a similar structure but with the different voltage levels and transformer arrangements. The wind turbines within the farm interconnected by the small medium voltage MV network, which is routed to a dedicated MV high voltage substation. The wind farm collects the power from the turbines at 33 kV and connected transmission grid via 132 kV circuit and the nearest 132 to 275 kV surroundings. As illustrated in the figure, a three-phase to the ground fault is assumed to occur one of the double circuit transmission lines nearest to the wind farm. The transmission system experiences zero voltage at the power point of fault and near zero voltage at the transmission substation until the line is cleared. The voltages at the wind turbine are suppressed but non-zero due to the interweaving MV connection in impedance and the current carried. The system frequency may become unstable, rapidly falling if the large numbers of generators are disconnected. The frequency fall may cause the cascaded tripping of the further generation units, leading to the forced widespread consumer disconnection to the widespread blackouts in a catastrophic failure. And here is a graph of three-phase balanced fault voltage profiles defined in different grid codes. During the fault and for the period of fault recovery, the plant must provide the reactive power to the support to the local network. Voltage and the active power must be delivered in matter of seconds following fault clearance. Such requirements are collectively known as the grid code fault right through or low voltage fault right through requirements. Figure 2 shows the grid code voltage versus time characteristics and specify the clearance times and the depths of the voltage dips that WTs must without tripping under the balanced three-phase fault conditions. Figure 2 also shows the non-international consensus on this issue since the FRT requirements are dependent on the different characters of the power systems in each the countries concerned. Overview of the test facility. The test facility was developed to experimentally evaluate the DFIG system under the range of grid fault conditions. It consists of five main components: a 10 kW direct current machine, wind turbine simulator, a 7.5 wound rotor induction machine, two back-to-back insulated gate bipolar transistor, power converts grid fault emulator, and a D-space based on the control unit. Figure 3 illustrates the block diagram of experimental test facility, shows a photograph of the setup. Here is a photograph of block diagram of DFIG test system. Wound rotor induction generator and the DC motor with the rotor shafts mechanically connected by the short stiff coupling techniques before the implementation on the test rig. To allow the rapid prototyping of the modified control scheme, the controller was developed in the proprietary MATLAB Simulink environment, which is automatically compiled and built the custom code of the operation on the DSpace controller. Now we are going to discuss about wind turbine emulator. The Higgs DC motor related to the 10 kW and 240 volt and 1650 RPM was driven by the 75A 4 quadrant control techniques mentor DC drive emulate the mechanical dynamics of the wind turbine. The control hardware within the drive executes software according to the mechanical model which replicates the torque input from the WT's rotor shaft. Turbine parameters are derived from the industrial data and the experimental measurements. Table 1 represents the mechanical properties of the combined DFIG rotor shaft. As the power engineers would do, We use the power we use per unit values in the paper express quantities and the fraction of the base value in which almost all cases is the rating of the machine. So the current share of the 0.5 pu half of the rated current. The value of reactive power of the 0.61 pu is 0.61 types of the rating of the machine. A voltage of 0.9 pu is 90% of the normal system voltage and so on. In these examples, per unit and percentage values are virtually are the same. Here is the table of wind turbine simulator parameters. However, things are slightly different when it comes to the impedance values. Hence, the per unit value of the impedance is the actual value of the ohms divided by the base impedance calculated as the square of the machine rated to line voltage divided by the rating of the machine. The DC drive has two modes of operation, speed control and torque control. To accommodate the wind turbine model, the device was set to the torque mode with speed control implemented within the wind turbine model. The WT model was used after successfully synchronizing the with supply voltage. The mechanical model was not engaged initially since the rapid acceleration would excite the poorly damaged resonance in the simulated drivetrain, causing the actual speed to oscillate wildly. To prevent the danger of overspeeds, a proximity sensor was used to estimate the speed and, if necessary, to trigger the emergency stop by a overspeed relay. The proximity sensor detects the speed of steel bolts and the nylon determines the generator speed from the sensor pulse frequency. Two measurements were initially carried out for the control purposes, a friction measurement and the inertia measurement. The friction measurement, the DFIG was unpowered, was driven by the DC drive with the machine's rated torque. Under no load condition, the DFIG quickly accelerated to no load speed. In theory, this speed was inversely proportional to the coefficient of friction on the first order lag speed graph, which allows the calculation of coefficient of friction. In the inertia test, the DFIG was given the rated speed held constant for a short period. Then the DC motor's power supply was interrupted by the DC motor contracted and the de-energized. The speed was recorded as the rotor coated to the standstill. The DC drive receives this analog torque reference from the D space controller via auxiliary input port and applies the appropriate armature current to the DC motor. By manipulating the armature currents, the DC drive can achieve the active torque control of the test induction generator, wound rotor induction generator. In this study, a 7.5 kilowatt Brooks wound rotor induction machine is selected for FRT analysis. The rotor of the induction machine was rewound to achieve the stator or rotor turns into the ratio of 0.32. Thus, the operational speed range of 0. Of plus or minus 30% in relation to the power converted DC link voltage. At maximum speed operation, magnitude of EMF is equal to the slater voltage, which corresponds to the voltage of the line slide (LSC). After viewing the new rotor's thermal rating is a 3.6 ampere phase, which is safely above the normal of operating requirement 3.35 ampere per phase. The induction machine parameters are detailed in table 2. Here is a table 2 of DFIG nominal and the measured parameters. IGBT power converters. A 415 volt 50 ampere purpose built IGBT power stack is employed as bidirectional back-to-back IGBT power converter. In the marketplace, commercial to the power electronics of the DFIGs are generally rated at the maximum operating rotor current to reduce cost. In this case, the power converter is specially overrated to prevent damage to the equipment when it is subjected to the grid disturbances. Similarly, the electrolytic DC link capacitors are also selected for their additional surge capability, permitting short-term excursions of up to 1.1 kilowatt per DC. A small three-phase choke is added to the rotor circuit supplement and the rotor's own inductance and limit to the pulse width modulation, voltage switching on the rotor windings. The RSC and LSC independently control 5 kHz and 4.9 kHz respectively. The converted DC link protected by the brake chopper, which discharge the DC link through the separate high power resistor. Clearly, the brake chopper can limit the DC link voltage during the grid faults by the converting the braking energy into heat. Now we are going to discuss about grid fault emulator. A grid fault emulator is used to produce a balanced grid faults with the voltage profile specified in the grid codes. They are applied to the terminals of the DFIG via isolation transformer. Figure 5 shows a schematic diagram of the grid fault emulator. The emulator is mounted in the two enclosures. Contactors, inductors, overload detection are installed in the large cage enclosure which are screen top and earthed on the motor housing. Here is the grid fault emulator setup. Three independent voltage levels are generated from the three variacs which connected by the set of back-to-back IGBT transfer switches. The magnitudes of faulty and recovery voltages are predetermined in the accordance with the acceptable grid code and the preset on the variance each test. IGBT switches are rated with the 55 ampere and are protected by the series of fast-acting 30 ampere semiconductor fuses. Status of the switched voltage sources is dictated by the command signal dispatched from the D-space controller. Also included in the grid fault emulator is set to the three-phase reactors which are selected as the representative lumped connection impedance for WT in a large wind farm. Now we are going to discuss about central control unit. The control hardware includes isolated sensors, analog protection with the interface boards, control development equipment, and dedicated computer. The success of the test facility is based on the DSpace DS1103 PPC single board computer, which controls the signal acquisition and conditioning wind turbine simulators simulating DFIG controller test, fault test, and protection schemes. Control signals are conditioned and routed through main board, which houses a peripheral interface controller microcontroller to perform the startup and shutdown procedures to respond the test rig error detection either by isolating appropriate sections of the circuit by activating the emergency stop. Test results. In this test, the DFIG was controlled to generate the unity power factor healthy conditions to export up to 0.6 pu of the reactive power to respond to the voltage drop below 50%. The VAR is a unit of the reactive power. Pre-fall conditions are consisted of the rated rotor speed, specifically 12% above the synchronous 1680 rpm and 67% rated power generation 5 kilowatt correspond to a typical operational charge slate. Zero voltage faults. The short circuit fault behavior of the wind turbine DFIG experimental facility shown in figure is the fault applied to the worst case 0.0% voltage fault is defined by the GB grid code. In figure 6a, the stator phase voltages show a rapid collapse in below 50 volts. The local voltages are maintained at the ground 30 volts during the fault. The most notable effects are the current spikes on the fault initiation and clearance. Similarly, reactive power increased quickly in the 6 kV AR after the fault initiation. The DFIC controller attempted to maximize the reactive output during the period of fault voltage. A 0.61 pu rotor reactive current on the rotor windings injected in the 0.14 pu reactive power to into the grid. That 0.16 pu stator voltages was maintained. The brake chopper was designed to the discharges below 795 volts, by which the time rotor flux has mostly decayed. At fault clearance, the rotor power surge created a second smaller DC link voltage spike. Here is a figure about DFIG response zero fault. 50% voltage faults. In figure 7.8, the stator voltages indicate the rapid collapse to approximately 0.65 pu. This level was maintained throughout the fault. In figure 7b, the stator current spikes touched the 22 ampere fault initiation and 17 ampere on the fault clearance, matching the rotor currents in PU terms. 7C shows the currents registered maximum spike of 7.1 ampere, 1.5 PU on fault in 5.9 on fault clearance. Here is a figure about DFIG response to 50% voltage fault. To date, the authors have used the rig to investigate the FRT performance of the DFIG with rotor prober and the brake chopper stator series dynamic brake resistor based methods. Thank you.